Hi everyone, my name is Stijn and I'm part of the technical product management team as part of the security technology business unit here, security networking business unit. And together with Chad, who's our global security technologist, I'll talk about how NSX Advanced Threat Prevention, or ATP, enables security teams to detect and prevent threats that go beyond the perimeter. So, before we get into the product, as we all know, security is not just the responsibility of a few. It's really everyone's responsibility, from our end customers, the end consumers that use the digital services that our customers provide, over our virtual infrastructure administrators who provide the platform for the applications to run, onto, of course, the firewall admins, architects, analysts, and CISOs. And I often talk to people that deal with security across these various different roles and across organizations. And specifically when talking to people that lead risk management, the top concerns that these people have are almost always the same. According to a recent survey, a very high number of executives are actually confident that their organizations can manage security risks. However, the top issue that keeps these security leaders up at night are threats from malicious actors, threats from hackers that keep using ever more complicated tactics and techniques in order to breach the organization's defenses. And if you know that a single breach costs an organization on average $4 million, it's not really a surprise that this is top of mind for security professionals. Security issues related to migration to the cloud, that kind of follows closely behind. And CISOs also see complex legacy data center infrastructure, as well as outdated security technologies and outdated processes, as well as too many alerts, or on the other hand, too many false negatives, with detection software as the key obstacles that hold their organizations back from reaching or achieving the security postures that they need. And this has forced 65% of executives to build security solutions in-house. So before we really dive into the product, let me talk a little bit about the mechanics of a breach. Of course, attackers first need to gain initial access into an environment. And this could be done by targeting users, the weakest link in the chain, which then download the malware from a compromised or spoofed website, execute the malware. Could also be done by exploiting a vulnerable service. Drew talked a little bit about that in the beginning. Or, as we've seen recently with the SolarWinds breach, the supply chain of a compromised or of a commercial enterprise application could be compromised, and a backdoor can be injected directly into the code of a signed update package. Now, once an attacker has gained initial access, once they've established persistence and command and control, then what we call active attack phase starts. And this is where attackers try to escalate their privileges in order to be able to follow through on their objectives. Attackers use techniques in order to avoid detection, things like when installing antivirus solutions. And attackers commonly use techniques like scanning in order to find other accessible surfaces within the network. Lateral movement is a very critical step. And this is where attackers try to use pivoting techniques in order to move from one system to another system. And this may involve, for example, the use of previously stolen credentials, the installation of remote access tools, or exploitation of services that are running on the remote host. The goal here for the attackers is to eventually gain access to the target system and the data that they're after which they will then exfiltrate the data. And that exfiltration often happens over obfuscated channels or using obfuscated techniques, for example, by using DNS in order to get the data out without being blocked by a firewall or without looking all too suspicious. Now, a couple of really interesting stats. While attackers may use the most expensive and the most complicated techniques in order to gain initial access into an environment, that initial target of an attack is almost never the actual objective. And this is illustrated really well by the fact that more than 60% of attacks involve some form of lateral movement. On average, it also takes more than 200 days for a breach to be identified. And this gives the attackers plenty of time and plenty of opportunity to extract what they need and to hide their activity afterwards. And attackers spend the majority of the time on that active attack phase that I just talked about, in which they're able to move laterally within the environment in order to extract the data that they're after. And this illustrates really well why internal security that is focused on what happens beyond the perimeter, what happens beyond that initial access, is really critical. Now, while everyone in security, spends a lot of time talking about the most recent 0-day, the latest breach, the sad reality is that in 2019, 60% of breaches involved unpatched vulnerabilities in which a patch was available but was not applied. And this illustrates another problem, which is the constant battle within organizations between security on one side and the speed of bringing up revenue-generating services on the other hand. So, now that we've kind of illustrated what the problem is that CISOs and security teams are dealing with, let's talk about the Surface-Defined Firewall, and specifically for our session, Chad and I will talk about the advanced threat prevention side of things. But as Dhruv and Brian already talked about, our Surface-Defined Firewall is basically made up of a distributed enforcement layer and then a unified management and analytics layer on top of that. Our distributed firewall, as Dhruv and Brian talked about, provides stateful layer 4 to layer 7 access control with port-independent enforcement using layer 7 application identity, as well as per user granular application access using identity firewall. And of course, as we all know, the goal of access control is to be able to reduce the attack surface, is to be able to limit the attack surface, as well as meet compliance. Now, the goal of ATP, or Advanced Threat Prevention, is a little bit different. Here, the goal is to be able to detect and to protect against threats that get through these allowed channels, threats that get through these open firewall ports. And NSX ATP consists of our distributed IDPS, which is fully integrated into NSX, into our distributed Surface-Defined Firewall, along with network sandboxing and network traffic analysis, or NTA, which came to us through the acquisition of Lastline. And then on top of that distributed data layer, we have our unified management and analytics layer with multi-site security management, providing a single pane of glass through federation, automated policy enforcement or automated policy formulation better through NSX intelligence, dashboards and alerts, and then network detection and response, or NDR, which comes through us from the Lastline acquisition. And NDR basically provides correlation of threat-related events from different individual sources like IDS and IPS, sandboxing, NTA, and it turns these individual events into actionable campaigns. And that makes the job of security operations centers a whole lot easier. So Dhruv talked about this a little bit before too, but what are the steps to securing modern data centers? First, of course, the easy steps, segmentation, implement segmentation using our distributed firewall. And very often, as Brian illustrated in his demo, our customers start their segmentation journey with simple zone-based segmentation. For example, between a dev environment, a prod environment, a test environment, isolating the workloads that belong to these different environments, and then gradually move to a micro-segmented architecture after that. Now, with a proper segmentation policy, customers can prevent lateral movement between these isolated zones, and customers can protect their critical assets by micro-segmenting them. After then reducing the attack surface by implementing segmentation, IDS and IPS can be applied again to that same granularity as where a distributed firewall sits, so to the VNIC of every workload, in order to detect and prevent against attackers that take advantage of vulnerabilities that may exist in applications or other malicious activity. And because of our position, and it's really a privileged position at the VNIC, it really doesn't matter if we're looking at an attacker who's trying to gain initial access into an environment, or a malware that is attempting to communicate out to a command and control server, or an attacker that is trying to exfiltrate data, or an attacker is trying to move laterally within a network segment, even within a VLAN. Because we sit at the VNIC of every workload, we see all that traffic. And then the third step is to deploy network traffic analysis, anti-malware, and network detection and response. And this allows us to extract files from the network, apply machine learning with threat-centric models in order to detect and then correlate malicious activity across the entire network. So let's zoom in to the advanced threat prevention feature set of our Surface-Defined Firewall. I talked about this a little bit. The NSX IDS and IPS provides per-hop threat intelligence-based detection and prevention. It's applied to every VNIC of every workload. And it gives us also the ability, as Dhruv talked about, to apply tailored signatures to every workload. As you know, IDS and IPS is very much focused on detection of threats, lateral movement techniques, and activity like command and control traffic. NTA then, or network traffic analysis, uses unsupervised machine learning in order to detect deviations from a baseline. And you'll see that in our demo as well. It also uses threat-centric models in order to be able to identify true threats from anomalies. An anomaly does not necessarily mean malicious activity, and we'll see that in our demo. And then anti-malware, and with malware analysis, this provides us with deep visibility into files and how they execute, and this enables the detection of not just known, but also new malware. And then finally, at the center of it all is NDR, or network detection and response, and this effectively correlates network traffic-based information from IDS and NTA with AI-based anomaly information from NTA and deep program visibility into the application from malware analysis into correlated and actionable campaigns. So with that, let's have a bit of a deeper look into each of these components that I just talked about. The key function of an IDS and IPS is to be able to detect and prevent threats over allowed channels, as I mentioned earlier. And allowed channels, they're basically just open ports on a firewall that ideally should only be open in order for the application to function. And while a firewall is really good at minimizing the attack surface, by only allowing traffic on ports that should be open, or by ensuring, for example, that we're only allowing TLS 102 across port 443, a firewall by itself does not prevent an attacker from exploiting a vulnerable service, a vulnerable application that may be running across one of these open ports. And this is where IDS and IPS comes in. So it uses IDS and IPS technology, uses deep packet inspection, or DPI, in order to not just look at the headers, but also the actual payload of a flow, in order to match those flows then against signatures to identify different types of potentially malicious activity. Think about reconnaissance attempts, malware activity, remote code execution attempts, command and control traffic. So, in the example in the slide here, you can see that we've isolated two different applications, and this prevents lateral movement between them. That's also what you've seen in Brian's demo. We can then, of course, also use the same distributed firewall that sits at the VNIC of every workload in order to implement the micro-segmentation policy. And within the multi-tier application, only allow the flows required for the application to function. We can even use layer 7 application identity on our distributed firewall to further reduce that attack surface and ensure that the traffic between the middleware and the database server, for example, really is the layer 7 protocol that it should be, and no other services can tunnel across that open port. Now, however, in order for us to be able to detect that an attacker is attempting to exploit a vulnerability, for example, here on our couch database server, we need intrusion detection and prevention capabilities. And I'm not going to go too much into depth about the architecture. We talked about this a little bit before, but a distributed IDS basically sits at that same position as our distributed firewall. It's also enabled as soon as you host prep a hypervisor with NSXT, meaning as soon as you install the NSXT bits on a hypervisor, everything that is required to run the distributed IDS sits there. You just have to choose whether you want to enable it on and then apply the appropriate policy. Now compare that to the traditional model where you have appliances, where you have to either split up your network into multiple smaller networks in order to insert a layer 3 hub, or you have to use span or tab in order to send a copy of the traffic to a dedicated cluster of IDPS appliances. We are completely network topology independent. It doesn't really matter, as I mentioned earlier, if we're looking at an initial attack targeting the front end of an application, or we're looking at ransomware that is laterally propagating over SMB between two VDI desktops. We get complete visibility into both the north-south as well as east-to-west tactics. And we support tag-based application, very similar to a firewall. If you need to apply an IPS policy, for instance, only to workloads that need to meet PCI compliance, or only to workloads in production, you can tag these workloads properly, and then you can apply an IDPS policy, which is then applied to these workloads, completely independent of which hypervisor the workloads are running on, and also completely independent of the network connectivity. And curated signature distribution, this is what Ruth talked about as well, so we can be very specific and only apply the signatures that are relevant. It doesn't make any sense to apply signatures related to a Windows vulnerability to a Linux workload, for example. So, here's a configuration example, and you see here I've created an IDPS profile for my database servers, and this only includes signatures relevant to the vulnerabilities affecting the databases that I've deployed in my environment. This greatly reduces the amount of noise or the amount of false positives. And as you can see here at the bottom too, I've then applied this IDPS profile in detect and prevent mode, basically an IPS mode, to only the workloads that have been tagged as the database server. So that means that regardless of where my database servers may reside in the network, regardless of how they are connected, the appropriate IDPS policy is applied.
So the database tag has to be applied to it. So say someone deploys a system, then installs a database on that, and they don't put the database tag there, the IDS, IPS signatures won't apply, correct?
It depends. So tagging is an option, Michael. You don't have to use tagging, but we see the vast majority of our customers that have dynamic applications that often come up really heavily rely on these tags. And you know, we see customers apply tags to identify that a workload, for example, is a database server, or that a workload is part of a particular multi-tier application, or that a workload is deployed in production and development. And then as a result of a tag, a workload becomes a member of a security group. And then you apply the IDPS policy to that security group. So tagging is one way of doing that. But you can also manually add workloads into a security group and then apply the appropriate policy, or you can even do it based on IP address if you don't want to use tagging.
Can you give us some more background on the IDS policy? So, of course, we have this curated policies that were coming from VMware directly. How are the capabilities of let's say self-developed IDS policies? Do you have an open interface for that?
So our IDPS engine is based on Suricata. So you know, we take signatures into the Suricata format, and our signature set. I know there was a question I think Dominic had asked earlier too. Our signatures sets are a curated set that is based on two other sets. It's based on the emergent threat set as well as the Spider Labs SLR set. And then with the acquisition of Lastline, we're adding our own curated Lastline signatures as well. And you know, I'm not going to go into too much detail, for example, but one of the things that Lastline does is when signatures are being developed, when, for example, malware runs in the sandbox and we see network connectivity indications of compromise from that malware, based on that, we can automatically generate new signatures. These signatures are then deployed in a test mode on existing sensors. And after collecting telemetry to ensure there's no false positives, to ensure you know there's no false negatives either, then these signatures are released and added to our set in production.
So just as a summary, when I deploy my own IDS policy, so imagine I have a team of people doing that, I can provide the right parameters and metadata that they will follow also your paradigm of setting just the right policy for the right devices, yeah?
So with policy, do you mean signatures?
I mean IDS policies in that sense, or signatures, yeah.
Yeah, so policies, you can absolutely define your own policy based on metadata. Things like CVSS score, CVE, things like the affected product, severity, things like the attack technique or the tactic or the technique, for example. You can include signatures in a policy based on that. And then you can selectively apply them where you want to apply to. You can also say that you want to apply that same policy only in detect-only mode to your workloads in development, for example, and then apply the same policy where you may already have done some tuning in detect and prevent mode to your workloads in production. So that means that when a workload gets promoted from development to production, you've already done the necessary tuning. Hopefully that tuning should not be a whole lot. And you can then safely apply the same policy in detect and prevent mode. Does that make sense?
Makes sense, absolutely.
Okay, perfect. So we looked at some of the configurations. So here's an example of an IDPS-based event. And the event at the top here shows that we've detected emotet command and control traffic going to our web VM1, from our web VM1 to a command and control server. And this traffic is going, of course, from the inside of our environment to that external C2, that external command and control server. So we kind of classify that as north to south traffic. Any IDPS that sits at the perimeter of a data center should be able to pick that up. Now, the example at the bottom is an example of east to west lateral movement within the data center. And in this case, the attacker was using cobalt strike beacons built in SSH client in order to move laterally to our couch database VM within the data center. Now, because the distributed IDS is applied to the VNIC of every workload, we can not only detect and prevent the event that we see on top there, the north to south command and control, but also that east to west lateral movement. Again, even if that lateral movement is between two workloads that are connected to the same network segment. So now let's have a look at our sandboxing. And what's unique about our sandboxing is that we use full system emulation in order to analyze programs. We're emulating the hardware, not just the operating system. And that allows us to see all the instructions that a process executes. Compare that to traditional sandboxing. With a traditional sandbox, you basically can only observe the interactions between a program and the underlying operating system. You don't get visibility into what happens with the hardware. Now, why does that visibility really matter? Well, let's have a look at an example. And when you look at the example here in the green, you can see the interactions that a traditional sandbox might observe. And you can see that the program under analysis, the program that we're analyzing, is asking the operating system for a list of running processes. It reads and it writes to some files, and then it opens a network connection. Now, who of you can tell me if this is a good or a bad thing? Well, it's really hard. It's really hard to know based on that. So let's kind of compare this to what our sandbox can see. And that's what you can see in orange. And we can see, in this case, we can see that the program is using that list of processes in order to check for a specific name, which is basically a string that indicates the presence of a traditional sandbox. We also see an individual CPU instruction that is often used as an evasive method. And we finally see that the program is using encryption. It's encrypting the data that it had read from those multiple files, and then it's using that encrypted data in order to overwrite the files. Finally, we can also see that we're sending an encryption key to a remote server. So clearly, with the additional visibility that we're getting by doing hardware emulation, it's a whole lot easier for us to be able to detect the ever more evasive types of malware.
What about the malware that will detect whether it's running in a virtualized environment or not? How do you handle that?
Yep, we'll get to that as well. We'll show you that, Michael, in a demo, and we'll cover that a bit on slides as well. We have a lot of different abilities to be able to detect evasive methods of malware that tries to detect it's running on a hardware sandbox, or malware that attempts to detect if it's running on a virtual machine. So, looking at an example here of malware analysis, you can see that through our AI-based anomaly detection, we've identified things like possible reuse of malicious code, and that helps us to detect new threats. Also through dynamic analysis, and by detonating the malware in our sandbox, we can also learn about the network behavior of the malware. And I mentioned this earlier. For example, we can see that malware is trying to initiate command and control. It's connecting or downloading additional malicious code. And we can then use what we learn here, use what we learn from the dynamic analysis, from the detonation of our malware, in order to automatically generate and curate IDPS signatures that then act on that network behavior. Now, here we can see hardware emulation, and you can see that hardware emulation basically allows us to detect malware, and it allows us to detect malware that is designed to detect by itself that it's running in a regular sandbox, and that would basically prevent detonation of the malware if it's running in a regular sandbox. So I'll have to speed up a little bit to make sure that we get to the demo, but let's have a brief look at NTA, or network traffic analysis. And we use, in our NTA component, we use AI, or artificial intelligence, in order to build models that allow us to detect malicious network traffic. And for that, we use a two-step process. In the first step, we apply unsupervised machine learning to all the traffic. And that allows us to recognize anomalies in traffic, anomalies from the baseline, that allows us to detect something from a traffic perspective is not normal, is not something that we've seen. The reality is, though, that that's not enough. Not every anomaly is a security incident or is a threat. So that's why we have a second step. And this is where we apply threat-centric models to these anomalies. And these threat-centric models allow us to identify the true threats and remove the noise, remove the anomalies that are not relevant to security. And this significantly reduces the amount of false positive. Now, sandboxing comes in very handy, again, as I mentioned, in order to train our threat-centric supervised models. We leverage the behaviors and the network traffic that is generated by analyzing all these millions of samples of malware that we're getting every day. And we also use our deep security domain expertise in order to make sure that the suitable algorithms are applied in order to build their models. And in the example that you can see here on the slide, you can see that out of all the noise that we were looking at earlier, all the different dots, all the anomalies that we've identified based on that, we basically picked out the anomalies like unusual SMB traffic that you can see on the left here between some of our desktops. And by then applying our threat synthetic models and by correlating this with signature-based events, we've determined that this was lateral movement involving eternal blue. Or at the bottom here, you can also see that NTA has determined that there was unusual DNS activity, which indicated an exfiltration attempt over DNS. And Chad is going to cover this in much more detail on in a live demo coming up. So
just a quick question regarding this. The processing of the machine learning, this is done in the cloud or locally processed?
So there's two options for that. So it can be done in the cloud, and we also have a standalone NDR SKU in which you can do that processing on-prem as well. So two options. Okay, so here's a quick example of some of the events that are based on network analysis. The top event that you're looking at here, for this workload, you can see that based on the baseline, we've seen some unusual behavior. And in this case, if you pay attention to the details, you can see that the workload performed a suspicious looking upload of a large file. This workload in general was not generating a lot of traffic at all. And suddenly we see a huge spike in the amount of data being uploaded. So that's something that we can learn through our unsupervised machine learning. However, the second event at the bottom, this shows not just a deviation from baseline, but this also shows that we're applying the threat-centric models to that anomalous traffic. And you can see that we've been able to identify an attempt at exfiltrating data by leveraging DNS tunneling. As you can see indicated there, it's kind of small, but you may be able to see it by all these different subdomains that are part of the different DNS queries. And NTA enables that discovery of DNS queries, for example, that look very different from the way that the normal DNS traffic that we're seeing from this particular host looks like. So before I hand it over to Chad, and I know I'm a little bit over my time, but let me summarize what we talked about so far and how our surface-defined firewall really changes the game. As Dhruv talked about earlier as well, traditional data center security is really implemented by hairpinning traffic to dedicated appliances, firewalls, IDPSs. And with this traditional approach, network topology changes are always needed in order to implement any level of segmentation. Even things like splitting up an internal network into different zones, into test, development, and production, for example. It requires a form of network architecture. Also, you need to hairpin traffic out on the physical network. And both of these things makes east-to-west security inside the data center very much impractical. And that leads to a lot of a lack of visibility and also really a lack of segmentation. Now, with our surface-defined firewall, we take a very different approach to data center security. And so instead of bolting on all of these different individual appliances, with surface-defined firewall, and with our distributed architecture, we deliver security controls in software like firewalling, like IDPS, and with the integration of Lastline capabilities, also Sandboxing, network traffic analysis. We deliver these directly to the network interface of a workload, completely independent of the network topology, and also independent and isolated from the actual assets that we're protecting. So we're not running any agents on the workload. That means that implementing visibility and security using the surface-defined firewall and using the security surfaces is really simple because we can provision firewalls on demand without having to install hardware, without having to make any network changes. And also because we have what we call application-centric dynamic security groups, this means that the surface-defined firewall enables our customers to basically tie the lifecycle of a security policy directly to the lifecycle of an application. So that means that when an application needs to scale up, you apply the appropriate tag to the application, and we automatically adjust the policy in the data plane to reflect the new reality without you having to make any changes in the management plane. The same is true with the other way around. You're decommissioning an application that is no longer being used. You don't have to touch the rules in the management plane. By virtue of those workloads not being there anymore, or by virtue of tags being removed, the policy in the data plane gets automatically reflected. So, with that, I'll hand things over to Chad, who will showcase our ATP capabilities in a few real world and live demos.
All right. Thanks for everybody. Again, Chad Skipper. I'm the Global Security Technologist here inside of VMware NSBU. Today, we're going to have two demos. We're going to start off with the second one on given time frame, and then we'll see if we have time to get to the original first one. But based on what Stijn was just saying, I'm going to provide an overview of what the advanced threat prevention looks like inside the data center, right? The ability to have these technologies, the Sandbox, deployed as a distributed service, as well as the IPS, as well as the NTA, actually brings together authoritative context that we can provide to you relative to campaigns, these intrusions that are bypassing, evading the perimeter, right? And then ending up inside of the data center. So all these technologies working together through many forms of machine learning, many forms of detection capabilities, really provide this context so that you can, have the authority with it to go off and apply either, response mechanisms or actually preventative capabilities. So what you're seeing right here is a campaign, and we're in promiscuous mode in the lab, right? This is all lab environment. This is promiscuous mode, but this is actually what we're seeing inside of our customer's environment. Everything that we're going to show you here has happened and does happen. So in this particular campaign, what we're first showing the SOC administrators, look, you have 5 threats that we have identified and correlated together. Now, these 5 threats here are anywhere from a malicious archive download, TrickBot, DRODX. I know these sound fearful names, but in this case, we have identified exactly what's going on in the organization, and it's targeting these 3 devices within the data center. Now, we also help you align these things by aligning the tactics, right? Not just the techniques, but the tactics that the adversary is deploying in your organization. In this particular attack stage, we saw delivery of something, and we'll show you what that is. From there, we began to see the command and control. This is the adversary communicating back with that asset in which he had a beachhead on. And then we see discovery. This is, again, the adversary discovering what's going on inside the organization, and then an exfiltration event. So the campaign blueprint, if you scroll down here, we actually give a very detailed campaign blueprint of what's going on inside of your organization. You can see here by the home icons that these are our devices within the data center. And here we're beginning to see some communication. Look at this. So we have DRODX as a command and control going between all of these 3 devices to this external device. We have TrickBot. Now, TrickBot is a banking Trojan. It's been around for years. It has multiple modularity capabilities within it, including things like DNSCAT and also DRODX, which is a remote access Trojan. And we've seen these really hop and scale in November timeframe. And then in January, because the modularity of it started attacking UEFI type components on hardware. But we also see here, if you click on the right here, we give this information, and there was a analysis report. This malicious binary download, the SIP archive here was downloaded by these 3 devices, and from there we begin to see DRODX's communication, TrickBot of these 3 devices, and then finally some DNS activity of exfiltration. But the blueprint's great, but what we actually want to provide is actually a timeline of everything that's happened, and then details behind that to provide the VI admin, the SOC administrator, that authoritative context behind it. So in this case, we can take a look at this timeline of what's happened during this particular breach. And you can sit here and you can look at the start time by end time, by the highest impact of these coming on. But we're going to start with the start time. And you can see here that we have this VDI infrastructure 12, and that user actually was able and actually was delivered a malicious archive download, right? So if we sit here and we look at this archive download, we see the potential capabilities. We see evasion capabilities here, and when we expand for more. But from this perspective, we know that .9 has downloaded this archive from this device. If we wanted to actually go and take a look and view more details around this threat, we certainly can, and this will bring up information specifically, on this on this particular threat, and we can dive in there and take a look and see exactly the analyst report. Now, imagine this having a reverse engineering on site for you, right? So this is the Sandbox report of what was going on with this malicious component. It was actually an archive. So the challenge with some of the sandboxes, they don't know how to understand some archives, right? So our Sandbox can detect over 150 different file types. And what we've seen in this particular executable, as we extract it, we understand that it was TrickBot. And here is where Stijn was talking about, and Michael, you asked about evasion techniques, right? Here is where we actually interact with the malware itself. And this is where we apply machine learning and unsupervised machine learning, and we can dynamically execute this and respond in kind with what the malware is wanting. And you can see here that from a virtual evasion standpoint, we saw the processor mode being switched from 32 to 64 bits. And this is really obfuscating it to try to trick sandboxes from actually inspecting these types of traffic. We see a little different masquerading. So that's the details that we provide just on this one event from this one campaign intrusion. The next thing that we see is now .9 is communicating. He's downloaded, he's got DryJacks. We see this command and control to 224, but we also see command and control here as well to this external device 119. But notice we see the verification has succeeded. So we're actually giving our analysts the ability to say, look, this is succeeding. We're seeing actual live communication right now between the threat actor and that host that was just compromised. Now, further on down, was there a question?
Yeah, I got a question for you.
Yep.
I guess this is the Lastline component doing the sandboxing, is it?
Correct. Yes, sir.
I have deployed the Lastline a couple of years back, and it was a lot of machines that had to deploy. So where is this running? Is it running somewhere automatically when you install all of this? Where are the sandboxes actually working?
That's a great question. So the Sandbox itself is working. We have two different deployment methods. One is hosted. So when, as an example, from a guest introspection, we see a file, we'll do static analysis, right? See it, whatever it is. If we don't know what it is, we'll send that up to the cloud, allow it to do dynamic analysis, and then from there we'll get further details that you've seen there. But we also have on-premise deployment of this as well. So that Sandbox can be deployed on your premise as well.
Okay, so that would be something that you have to do if you set all of this up. Do the on-prem deployment.
On the on-prem, you would, you would set this up as an on-prem deployment, and you get the same capabilities, but everything stays on-prem.
Okay.
Even the dynamic analysis, because you can put that Sandbox on your premise. So moving forward here, so as an example, this is Sandbox. Now be in mind, this is all promiscuous right now. This could be inline, and we could block this from ever being delivered to your user, right? The malicious download. Now, command and control in prevention mode, naturally, it can prevent it. Now, moving forward, this is where NTA comes in, right? The discovery here that we see this unusual network behavior of a suspicious session, it's a enumerating process. So now we see .5, 45.9 enumerating processes against this internal host here, 45.15. And then we see the same thing here. 15 is now downloaded this file. We see communication, it is moved laterally. And then we see again discovery from VDI 13 to 221, which is actually the health app, right? This health app that we put up. And so now we've seen this pivot. I had initial access inside the data center. I moved laterally, download more malware, move laterally to where now I'm on this health app, and we see this DNS exfiltration. So this is another area where, again, we have sandboxing here. We have IDS, IPS being able to detect that communication, pulling this all together, and we see an exfiltration event. This is an anomaly event where we see using DNS cat exfiltrating data over DNS, which is another way that adversaries obfuscate and evade and moving their data out. Now, all of this, if you take a look in the distributed nature of this, imagine having, individual siloed components, each individually alerting on this, and you really wouldn't understand the full effects of the entire campaign. Now, I will close with one. I know we're at the bottom of the hour. I will close with the last demo. The last demo is purely east-west, right? This is our ability using unsupervised machine learning to understand what's going on inside the data center, right? You're not only protecting ingress and egress, but you're also protecting those anomalies and the threat actors that end up bypassing and getting inside the environment. You're looking for that those anomalies. And here, using unsupervised machine learning and understanding a baseline, it usually takes about 7 days to get a baseline of traffic inside of your organization so that we have an understanding. Here, we're noticing 4 anomalies that are impacting 3 hosts inside of the organization. Now, here again, we've got lateral movement. That's the only tactic that we're seeing across this particular attack stage. But paying attention here, you can see our home devices, all of our inside the data center, but we're seeing anomalous PSX interaction. That's against the baseline. It's anomaly. We haven't seen that before, but we're pulling all these together because at the same time, we've seen this device try to do a remote task scheduling to 100 using suspicious tickets from Kerberos. Then followed this by RDP connections. Now, RDP is a dime a dozen within the organization. A lot of folks use RDP. We understand that, but this is where the unsupervised machine learning comes into play, because we're applying, saying, look, we've never seen a lot of RDP connections between these 2 devices, and all of a sudden we see this anomaly. So now we're bringing together anomalous activity inside the organization so that they can go off and rectify that. And naturally, we still have, we still have the timeline series here as well. And you can take a look at that timeline from start, where we can see all of this lateral movement. This is our internal network management software. All of a sudden, we're seeing some unusual traffic of it connecting, as an example, to 101 here, using a suspicious RDP to a management system within the organization. So in closing, I hope that you can see from an overview perspective of what we've talked about is the distributed nature of the advanced threat prevention capabilities, the IDS, the Sandbox, as well as the NTA, and those correlating together from a network detection response capabilities really provides some great authoritative context for our users and our customers to prevent those advanced threats from entering and operating within the data center. So with that, I'll turn it back over to you, Tom, and see if we don't have any closing questions.
Just a quick question, Chad, on that one. How long can you store this information?
Store what type of information are you speaking of? You're talking about, so we store the flows, right? The flows themselves. I know we store them for 30 days, up to 90 days. Anything other than that, we'll have to add expansion, but that's as long as we store those flows.
Can I scale up with just more additional storage to store them longer, or your system is limiting me to these 30 days?
No, you can expand as you wish.
For example, you had as an example the SolarWinds case, yeah, which was more or less 1 year ago, yeah. Would be great to have these data available for something that happened 12 months ago, yeah.
Absolutely. We have those capabilities to scale up and save that data. The DNS activity alone, right? The DNS activity of the SolarWinds and being able to understand, did I ever see that beacon out going to these IP addresses, be able to research and look at those from a flow perspective. Stijn, did you want to add something?
Absolutely. I think SolarWinds is a really good example. If you've installed that vulnerable update of SolarWinds a year ago, a long time ago, then the question is really now going back, what happens? How far can I still scope the compromise? How far has it been assumed that you've been infected, right? And then having that data, the ability to go back in time in order to determine that scope, that's really crucial.
Yep.
Plus, another thing to quickly add in there, isolating is really important and really easy, right, with the distributed firewall. So if you know that you've installed, SolarWinds, you have these compromised assets, quickly isolating those from the rest of your environment without having to make any network changes, without actually having to insert a firewall. It doesn't matter where these compromised workloads reside. You can quickly apply a tag and isolate them from the rest of the environment. Right. Is one of the key benefits that we get with the distributed architecture.
Yeah. So at this point here, segmentation would have helped in stopping that lateral movement from your network management system to wherever other aspects within your organization.
When files get sent up to the cloud for analysis, is there any way to limit a subset of systems to where they don't? Say you've got systems that are for proprietary, highly sensitive product you're working on, and you don't want anyone to know about it yet. Can you have where those files stay locally, but your currently production stuff sends stuff to the cloud?
I don't think I think it's a one set all since we're on as I'll have to get back to you that on Malcolm for sure. But, since we're introspection and we're on the wire and we're going to either be, looking at it from the distributed standpoint, we're going to have access to everything. So we're going to push everything up to the cloud for dynamic analysis or on your premise for dynamic analysis, if that's the case. I'll get back to you, but I don't think we have the capability to segment out based on device what data is being sent to the sandbox.